we know that you got a point here, got an electric field going out, and so I want to know what is the voltage difference here if I go from here to there, for example. So from R1 to R2. Okay. Well, we know that the difference in voltage is going to be minus integral of E dot ds. Okay. Well, in this case, the difference in voltage is going to be minus integral of kq over r squared times dr. Because the dr, because I'm going straight outward, so my ds is going to be my dr. Okay, well, this is pretty straightforward. This is equal to minus kq integral dr over r squared. Okay, so r squared, and we're going from R1 to R2. Okay. Difference in voltage is going to be equal to KQ 1 over R squared, or rather 1 over R, evaluated at R1 and R2. Okay, so that would be delta V is KQ times 1 over R2 minus 1 over R1. Okay. Now, for my point source here, some Q, and I'm going out this way, let's take a limit as R2 goes to infinity. So what is the difference in voltage from that point R1 to infinity? Well, that's going to be equal to, if you take the limit there, the 1 over R2 term goes away, so that's just KQ over R1. Okay, so that's the difference in voltage from here to there. Okay. Okay. Well, minus that. Okay, because it's minus. So what does that mean? Well, it means I ended up decreasing voltage by that amount to go to infinity. So the next question is, well, what is the, remember, voltage is kind of an arbitrary sort of thing. Okay, so what's the electrical potential at infinity? Okay, well, we can define it to be anything we want, and if you're infinitely far away, you're not likely to interact, so we could call that 0. So that means that when I went away from my charge, I started here at some r, let's forget about calling r1, just call it r, and I went out to infinity. What I did was they changed the voltage by kq over r. Okay, so that meant if it's 0 out here, so that was the change in voltage, was a drop. So if V is 0 out here, then what was V here if I drop by that amount to get to 0? Well, it's pretty simple. KQ over R. Okay. And so we would then say the electric field due to a point charge, we got a point charge right here. Here we are some distance r away from it. The electric potential at that point is going to be KQ over R. Now your book writes it as 1 over 4 pi epsilon naught Q over R, but we know that is exactly the same thing because 1 over 4 pi epsilon naught is in fact the electrostatic constant, K. I just like to write whichever has the fewest pen strokes. So now we have an expression to describe this. Now here's the interesting thing. That's a scalar. Okay. That's not a vector. That's a scalar. So that means if we had two charges right here, and I want to know what is the electric potential right there. Well, that's simple. All we got to do is figure out that R1, figure out that R2, and this is going to be KQ1 over R1 plus KQ2 over R2. In fact, I could have a whole bunch of charges here, and I got some spot over here, and so I want to know, what is it for all these? Because it's a scalar, then all I got to do is add. So that means this is just going to be the sum, n equals 1 to however many there are of k q sub I, or q sub n r sub n. That's it. Okay, so this is how you'd find the electric potential. The nice thing is it's a scalar. Scalars are always easier to work with than vectors. So this is how we would do it. In fact, since finding the electric field is a derivative, derivatives seem to always be easier to me than integrals. And that's true for a lot of people. And so what often happens is, if people want to find the electric field, what they often do is they figure out the electric potential first and then take a derivative.